So we are live. Okay, those are working. Let's check this. Please have data soon. Okay. LinkedIn is up. Okay. Let's go ahead and pause the video. Yeah, no volume. We do have a bit right here. Okay. This one doesn't include a page. Yeah, that's fine. Okay, preview. Fresh. Okay, pause that. Pause that. Crazy. Let's go ahead and say hello. Say hello. Hello, Twitch. Okay. Oh, I haven't gone live yet on that. Okay, yeah, let's go ahead and go live. Here. Okay. They do comments on that, so I don't even worry how to comment below. Paste. Okay. Okay. Okay, let's turn off right now. We can turn. Okay, everything's looking good. How are we doing? We got like 8 people across all the streams. That's good. Welcome. We'll start here in a few minutes. Just like setting up the stream early just to make sure everything's working. But yeah, feel free to say hi, where you're from, your interest in FPGAs, or the topic today, it's Spartan UltraScale Plus, or the AMD MicroBlaze V soft processor. I'll try to get to the questions now or during the stream. Oh, I jumped up. Okay. If you joined in the last minute or two, we're just going to wait a few minutes to start the stream, but feel free, say hi, your interest in FPGAs, any questions, and we'll try to adjust it during the stream today. We're just setting up the stream early to make sure the multi-streaming and chat is working, audio is working. I do not know the latencies on the various platforms. I will try to adjust the questions in a timely fashion, but we're doing a speed run today, so I may be a little bit focused on the content, but there'll be pauses where we'll be able to try to answer any questions in chat or comments. Okay, we'll reply to that chat. So we have a question from LinkedIn. I'll have to describe that vocally. Do you show how to connect MicroBlaze to DDR2 memory? So the platform we're doing today does not have any external DDR memory. We're going to be only using the local VRAM within the FPGA. We'll be looking at HyperRAM in the future, but with the Spartan UltraScale Plus development board, I do not have the DDR2 memory modules to be able to demonstrate that connection. Okay, it is 8:30. We are up to yeah, about 12 people. Okay, so let's start. Hello to the stream. We are starting. This is going to be a live demonstration, so hopefully all goes well and nothing breaks. But we'll be looking at the Spartan UltraScale Plus from AMD, one of their new FPGAs they just announced for their production runs. We'll be implementing the MicroBlaze V, a soft RISC-V processor into the FPGA. We're going to do this as a speed run, so we're going to try to time it. And this any percent speed run is we're going to look at the minimum viable functionality needed to get a hello world on the system. So thank you for joining us. And yes, once again, feel free to use the chat. I'll try to address it when I can. So some disclaimers. I am not employed by AMD, and this is not a paid stream. AMD loaned me this board to explore its features. I do not offer official support for these products. Note, if I use any links, there may be some analytical collection for them, but I do not get any commissions off the links for this stream. The content on this channel is created for informational purposes only, and all the opinions expressed on this channel are my own. I go by FPGA Zealot on various different streams, or very different social medias, YouTube, X, Twitch. There's a Discord server link as well if you want to chat more about FPGAs. I also go by Andrew Wilson on LinkedIn. So I'm going to go ahead and turn on some other features that we have running. So I just turned on the speedrun. I just turned on the camera for the board. So let's dig a little bit into what we're working with today. So we're going to be looking at the AMD Spartan UltraScale Plus FPGA. So this is going to be the smallest available FPGA on their 16 nanometer process. And recently, a few years ago, they announced the Arctic UltraScale Plus, which is kind of in a similar space. The Spartan UltraScale Plus does offer some new intriguing features, which we'll talk about now. So today we'll be looking at the SCU35P, a smaller variant, and doesn't have all the features that are available in this family. But we do, what's the word I used? We do backport some features from the Versal FPGA family in their 7 nanometer process. Well, it's not from their newer FPGA, the Versal. We do backport some really useful features for performance, security, and reliability. So I'm going to post a link in the chat. I'm going to jump to this link real quick. And this is the website from AMD that's going to talk about the Spartan UltraScale Plus. And we're going to scroll down to the block diagram to talk a little bit about the features I want to point out today. So from the Versal, they're backporting the IO bank called XP5IO, and this bank includes a hardened DDR controller. And this hardened DDR controller supports up to LPDDR4 and 5. And I think that'd be very useful. There's also security and reliability features that are implemented as a platform management controller. And then they have high-speed transceivers, the same one that are kind of available in some of the R6 UltraScale Plus families, to 16 gigabit per second, supporting PCI Gen 4. To look into more detail of the different product families, we have the product selection guide here. So the 35P today has 32K flip-flops, 16K LUTs, 1.7 megabit block RAM. Then we have the high density IO that goes up to 3.3 voltage, and then the high performance. What was the max voltage on it? It was either 1.8 or 2.5. I'm not sure. And we're looking at one of these packages. Oh yeah, this package, I think. So the other features that are on the larger variants, we have the XP5IO bank here, which includes the integrated memory controller. And then we have the high-speed transceivers at 16.3 gigabits per second that support up to PCI Gen 4. And you can see which variant and package is required for these interfaces. There's also UltraRAM, which provides more internal memory to the FPGA on the two larger products. Okay. So I want to take a moment to talk about the platform management controller that's in the Spartan UltraScale Plus. So this is a small processor that provides additional security and reliability that is on the Versal. The cool thing about this is that they kept all the UltraScale Plus low-level primitives. So if you're going from one UltraScale Plus design to this design, those primitives will still operate. There's just going to be a kind of a middleman, a processor below that still supports the same feature set but includes more feature sets. We're having a superset. We're not removing any features. We will not explore this in this video today, but I want to explore this in future videos because there's a lot of cool stuff here. So today we'll be targeting the development board, the SCU35 for the SCU35P. Okay, here's the package. We're doing the 625. And this includes some basic USB JTAG and UART. We have a 100 meg Ethernet, QSPI flash, and HyperRAM for kind of our basic modules on the board. And then for external interfaces, we have Raspberry Pi 2, Raspberry Pi Hat, an Arduino Shield. We have the DigiLink PMod, which is has a great catalog of different systems. And I like this one because it allows you direct connection to the IO, so you can do different protocols. Next, we have the high-speed IO port here. This is pin compatible with the Syzygy standard, but does not include the auto voltage negotiation. So if you do use any Syzygy daughter cards on here, make sure you're following the standard IO layout, so we don't have any high-speed transceivers. We're just doing basic IO, and that your voltages match from what's being delivered from the development board to the daughter card, so that it functions properly and there's no potential damage. And you can find the list of Syzygy cards here, as well as there is an Avnet dual camera high-speed IO module. Be sure you check the schematics when you do this, that they're using the standard IO and not the high-speed transceivers. There are slightly different connectors, so make sure you check the schematic that it's compatible with the hardware you're looking at. The last interface to talk about, which I haven't used much, but I'm really surprised by, is the MicroE Click. So this includes, if you look right here, this includes a UART, a SPI interface, and an I2C interface. And then there is a massive catalog, right, of over 1,800 boards, which include various different functions, wireless, memory, motor control. I really want to look at these more, so I plan to purchase some for myself so I can explore these different expansion cards. Okay. So here are the the I/O banks for this board. We have the configuration bank, which that platform management controller is micromanaging. We have JTAG and the QSPI flash, the mode pins, and then we have the high density pins, which are handling most of our external interfaces and our Ethernet. And then the high performance bank here, which is handling our hyper RAM that can go up to 200 megahertz clock rate. And then we have our high speed I/O interface as well in the high performance bank. For today, our development environment, the computer I'm working on right now is an AMD Ryzen processor. We have 32 gigs of RAM and a standard M.2 SSD. I'm doing this on Windows, but you can easily do this on Linux. The tools work basically the same. We are using the newest Vivado 2025.1. This is free, and it also includes a free license for this FPGA and development board, as well as additional board support information for it. We'll be using Vitis, which is the software IDE, which is included with Vivado. Our target today, or our design target, is the MicroBlaze V, which is a RISC-V processor, which adheres to the RISC-V instruction set architecture standard. So any RISC-V compiler, application library, and stuff like that, we can use here. So this allows us to utilize what's already on the open market. There are also additional ISA extensions specific for the Vivado, this Vivado implementation. One of them is AxiStream processing, and it allows you to do some nice tight connections between the processor and the AxiStream IP cores that are available from Vivado. I would love to demonstrate that in a future video, but it's a really cool way to quickly process stream data. So our speed run today, so we got all the background information now. Let's talk about what we're going to do today. We're going to open Vivado. We're going to set up the project, implement the design as a block diagram using Vivado's IP repository. Then we're going to generate a hardware export as an XSA file to the Vitis software IDE. We'll be generating the the platform via board support package, which provides the software libraries for the MicroBlaze processor and the various IP driver software. Then we can generate the application ELF that we run on the soft processor. And then we're also going to generate the bitstream, which is going to be a PDI file for the Spartan UltraScale Plus, which is similar to the Versal FPGA family. We're using the board files. These board files are specific for the development board. They provide us the various interfaces that we can easily add in the block diagram, and contains the pin and I/O constraints so that it's very easy to quickly implement the bitstream. Once that's all done, we can run the hello world on the actual hardware. Okay, I'm going to open up the hardware and plug in the board. So feel free to ask some questions and we can answer them before we begin the official speedrun. Okay, let me change the camera so you can get a look at the board. So here's our board, right? So the camera. So first we're going to plug in the FTDI chip with the micro USB. This includes JTAG and 3 different serial UARTs. And then we're going to plug in the power. The power is going to turns on. This is the voltage negotiation power delivery system for USB-C. We're using 20 volts at like 2 watts, or yeah, about 2.5 watts. Okay, we're going to go back to our normal screen. We have Vivado up, and we're going to begin the speed run. Let's make sure there's nothing in chat. Okay, so let us start. So we're going to open up a new project. We're going to call this live. We're going to do an RTL project. We're not going to do any HDL sources at this time, and we're going to do a standard Vitis platform and not use the extensible features today. So if we go to boards, I have the Spartan board that's included with the Vitis install, Vivado install. We'll hit next and we'll finish. Okay, now moving on to the next thing, we're going to create a block diagram. I like to call this top. So in the board section, we have our various inputs and outputs. We're going to add the clock as a clocking wizard, which will use the MMCM that's available on the hardware. With the clocking wizard, you can choose between an MMCM, RPLL, or let it decide. There's also a lot of other additional features that you can utilize. We're going to turn the reset off. I like to have a continuous clock in my system. Especially helps with debug if your reset is being held. So for the UART, its default baud rate is 9600. I'm going to increase that to a kind of a more standard baud rate you see on like a Raspberry Pi. And next, we're going to add IP. We're going to do the MicroBlaze V. We're just going to click block automation, and this gives us some quick settings that we can change. You can also double click the block to do additional, more advanced settings. And then we're going to connect the UART to the data peripheral bus and the reset. Next, we're going to validate. This is going to check our addresses, our PCI configurations, our different bus interfaces, that everything is good for implementation. Then we're going to save. Once the save is done, we can go over here on the sources, right click, and we're going to create an HDL wrapper. We're going to let Vivado manage this, so if we add any inputs or outputs, the top level will be automatically updated. Once that is done, we are finished with the top wrapper. We can go ahead and generate our device image. And it's going to kick off a bunch of different parallel runs for the blocks, parallel synthesis runs for a bunch of the blocks in the BD, and then go to synthesis, and then implementation, where it's going to do placement and routing, and then finally generate the bit stream. Okay, so here are the various blocks. I'll open up the local memory in a second once this is in the background, and then we can look at how the processor is connected to the local memory bus. We have a smart connect that is connecting the RISC-V AXI Lite data peripheral to the UART that we're going to use for standard in and standard out for our application. Oh, the speedrun timer lets me see how delayed the stream is. So let me just crack this open real quick. Regenerate. So we have our local memory buses, which are on a unified memory controller. So the instruction data will be using the same memory space. So let's go ahead and export our block diagram as an XSA file for the Vitis software IDE. And it's done. We can go to Tools, and we can launch the Vitis IDE. Okay, it's opening a little smaller. Oh, you have to extend. We can move to the next step. Okay, so opening us full screen so everyone can see. We're going to set the workspace. And we're just going to jump to our project folder. Live. We're just going to create a folder for our workspace. I just call it SDK. You can call it workspace, WS, whatever makes sense to you. Once that has been set, we can begin generating the platform. So we're going to generate the platform component. This is going to create our software BSP, including our libraries for the MicroBlaze and various drivers. There are a bunch of, pre-configured ones for other development boards, usually those with hardened processors. But we're going to select the XSA file that we just exported from the Vivado project. Right here. hit next. And then it's going to look through our XSA and find any processors. We only have one, the MicroBlaze RISC-V. So once that's done, we can generate the platform. And then we can look through a few files. We have a few moments as the bitstream is being generated in the background to take a few moments to look at more details that are in the platform. So I want to look at the sources real quick. So under hardware, or no, under the include, so sources, MicroBlaze, standalone, BSP, include, there's an X parameter. So this is basically all the settings that are being imported from our block diagram. It includes our Axi interface, includes the baud rate configuration. So it's a software, or I'm not sure this is software configurable. Look at that. Also includes all our MicroBlaze RISC-V parameters if we use cache or other ISA extensions. The other thing to look at is this lib source, which includes our driver for the UART Lite. I particularly like looking at this header file. No, it's this by the L.H header file. And this includes your register offsets. This also includes the bit masking for those registers. So very useful. Okay. Next, if we look at the JSON here and we open up the standalone board support package, we can see that there are various libraries we can add. There's also settings, so we can change the standard in and standard out, add some other features. Another thing to note is the drivers right here. It takes a moment to bring this up. It will have a section for every IP core that you've implemented. And you can easily look up the documentation, and you can easily import software examples, which I find very useful. Okay, so now we can go ahead and build the platform. For the MicroBlaze, it's relatively quick to do the platform. If you've done this with other Zinc, UltraScale, Versal devices, the platform has more extensive board support package. So right here, we have examples. We're just going to do the standard Hello World example and create an application component. And we're just going to select the platform we built. We're going to select the MicroBlaze RISC-V as our target and finish. So let's look at some files in here as well. Up here. So the first thing I want to look is the linker script. So right now we only have one memory region, which is the the instruction and data local memory, which is only 16 kilobytes. We have a stack size, a heap size we can adjust. We can also adjust which memory each of these application components will be loaded into. So we have multiple memories, our other stuff, we have some fine-tuned control. And it's nice to have this GUI. Writing a linker script from scratch is relatively difficult. And then we have our application, which is going to send hello world on the standard out. Okay, and then we can just hit build. I'm only going to build the application. I don't need to build the platform every single time because my drivers are not changing. And this will allow for quicker development cycles of me rapidly building the application only. So I'm going to save this in the workspace preferences in case I want to change it later. And you can see here that there's only a few files that need to be compiled, and we're done. We have our software is ready to go. Let's go check in on the hardware. We are in the initial design space. We can track that here, where the log file is being outputted. Well, let's go ahead and open up the synthesized design to look at a few different features. Go ahead and like some comments, I guess. Okay. So yes. Okay, Varbon on YouTube asks, are there examples for multi-core designs with MicroBlaze 5 and programming with and without NUMA? I don't know the NUMA acronym off the top of my head. I'll have to, maybe I can look that up real quick. NUMA. What do you mean in this context? I don't know about the non-uniform memory access at the moment. But it sounds like a multiprocessor thing? No, it's not. Okay, so yeah, I don't know of any good examples for the multiprocessor at the moment. But you can instantiate multiprocessors, do your own mailbox system. There's nothing preventing you from doing multiple instances of the processor. Okay, thanks for the question. Oh yeah, you can modify the memory spaces for each processor separately. Yeah, you have that that fine grained control over the processor. Okay, so here's our package right here. We only got a few minutes before the bitstream is ready. Here's our different banks. If we go to properties, we can see we have high density banks here. This is our one high performance bank, and the rest of these are high density. We can bring this up and we can look at our pins. We have the reset. We have our UART out and in on this bank. Then we have our differential clock input right here. And we want to look at the constraints that are being used. We can edit timing constraints. And these are all the timing constraints that are implemented by the block diagram and the various IP cores. And they will be used for doing timing in synthesis and implementation. Next things, I wanted to report utilization and show how much this processor and UART are using. We can go ahead and go to the summary. So we're using about 10% of the FPGA at the moment, with the 16K LUTs and the 32K flip-flops. The LUTs being lookup tables, the flip-flops being the 1-bit registers. VRAMs, these are about 36 kilobits of data. We're only using a fraction of the I/O. And the MMCMs, in addition to the PLLs, give us our clock generation, and we're using one of the two that are available. So now let's go look at the schematic. This is the net list. And we can go dig into the design. I want to look at the UART here. And if we look at the Axiolite interface, we can see the various LUTs and flip-flops that are used to define the logic and the design that are currently being placed and routed to it. Even if we click here, let me see, go to cell properties down here, we can actually look at the truth table. I can't really zoom in. So this is the truth table for that LUT. And we can look at the various LUT 6s, LUT 4s, LUT 3s, and these LUTs might be packaged together as one LUT 6. We can maybe look at that later. Okay, so we are in the right bit stream, so we're almost done. So let me get set up for programming the board. We're gonna get TeraTerm connected to that FTDI chip. So there's 3 UARTs. I'm going to be using the first on port B. We're going to then change the baud rate to this setting. Okay, we are getting close to go. Okay, it's going to take a little bit to finish up the last bit of the bitstream generation, but feel free to ask questions. Okay. Oh. Why is I bet okay. Live streaming may have affected my timing. Okay, let's go ahead and open the hardware manager and try to get this done in the next 20 seconds. So the board appears, we're going to program it. Doesn't take long. Then let's run the application. Oh, we don't need that big. And we are done. Okay, so we have successfully implemented a soft processor, used the software IDE to set up a Hello World application in about 15 minutes. As we wrap up, I want to look a little bit more at some of the debug and reports that are available in Vivado. But thank you for being here so far. I think this is a great opportunity to show what is available on these FPGA systems. So I want to open up the system monitor real quick. So I'll show you what is available over the JTAG telemetry. So we're just going to add the temperature and the 3 voltage banks. I seem to have missed the OK button. Oop. There we go. Okay. And we can monitor the temperature and the voltages on these banks. Giving us some live feedback. We can change the scan rate and the track time. I use this when I want to see how the board affects the power of or the design affects the power of the board. Let's go ahead and open up the implemented design and look at a little bit of the results of the generation for the design. So let's scroll up a little bit. First, we're going to look at the timing report. We have 5 nanoseconds of slack, plenty of slack. We could probably bump up the speed of the MicroBlaze to 200 to 300 megahertz. But if you click the slack, it will go to your worst offending nets. And you can right-click these paths and open the schematic view. You'll see the input flip-flop and the output flip-flop. These are hidden because they're part of the MicroBlaze logic. We can also go to the power. We have the device static power, which is based upon more of our placement and how much we're using in the placement for design. And then we have the static power, which is going to be based upon the clock rate and how many routes we're using and the toggle rate on that. And we can also, break down and look how these things work. You can change the various settings depending upon which environment you want to do. It's useful to get a better report on this. So let's go ahead and look at the utilization of the device. I think it's about the same, but we can look at how it's placed and routed. Yeah, it's about, we were able to pack some LUTs. So we got a better LUT report, and we're doing some LUT RAMs here that weren't reported in synthesis. Okay, so the net list here, we can see the top level here. So let's go ahead and zoom in on our implementation. We can highlight the MicroBlaze processor. We can highlight the local memory it's using. Here, it's scattered a little bit around the design. We can highlight the UART. Light blue. And then we can do the smart connect that's used as an AXI light interconnect. We're going to do red for this. Okay, so that's kind of how our place and route design is. And we can zoom in, look at one of these interfaces. So this is our logic slice. It includes 6 LUT 6s, or no, is it 7 LUT 6s and twice that many flip-flops? No, it's 8 LUT 6s. I can't see that one right there. 8 LUT 6s and 16 flip-flops. And you can, once again, click on these. If you go to the LUT, you can see cell. Yeah, here we go. We can see the, oh, not on this one, it's hidden. But we can follow these nets through the routing mux over here and see how it goes through the design. I want the routing mux, not a net. There's our routing mux, and there's the various nets in here. Okay, so let's jump over here to the I/O. I want to show this real quick. We're going to grab the 2 pads. We're going to open up the schematic. And we have our input and our output. We can trace these to the various systems. And refresh. Okay, so this is our UART light. This is our input of the UART and the output. We can see the buffers that are being utilized. That's about all I can really show today with the data that comes out of the Vivado software, which I find very useful for a lot of the stuff I've done at work and fun and academics. Okay, so let's jump back to our presentation. Okay, we have a question real quick from Rishi on YouTube. Have you tried using two RISC-V processors? How does the Vitis IDE handles that? So the Vitis IDE identifies these as two separate processors. So you create two separate domains, and then what you can do is you can have an application per domain, and it's very easy to then just target that application, modify that application for that specific processor and change it. You can also easily switch which domain or which ELF file goes for which processor. There's a lot of nice settings for it. Lockstep for MicroBlaze 2. There is a TMR, there is a triplicated MicroBlaze that's really easy to do. I do not, off the top of my head, know what IP there is for a lockstep. I do think you can do it. I'm just not sure off the top of my head which IP is available. That was another question from YouTube. Thank you for your question, guys. It's great. So, I want to talk about the HyperRAM real quick. There's only 1.2 megabit of internal VRAM memory for the RISC-V processor. And if you want to have a more complex software application or using like video frames or whatnot, you need to use the HyperRAM. So in future videos, I really want to look at using the HyperRAM and be able to do Ethernet, video DMA, and be able to show a little bit more interesting applications on this board instead of, you know, basic hello world. So hopefully join me on the future videos where we look at that. Once again, look at the link in the chat. Let me add that link in the chat over here. To learn more about the Spartan UltraScale Plus, the link in the chat will take you to AMD's page on their new FPGA. The dev board, they don't have that listed at the moment, but they will be releasing that in the coming months. Okay, we are closing up. We can take a moment and look for the MicroBlaze lockstep. Let me look. It might not be implemented for the RISC-V yet. So where is this? This is a MicroBlaze architect question. Okay, so let's go look at that real quick in Vivado. I think we open up this, make this a little bit smaller. Okay, cool. I think the last page, breakpoints, interface, lockstep right here. Okay, we do have lockstep. We can do lockstep master, slave, and hidden slave. Let's go ahead and open up the documentation. So we can hit the product guide, and this is open up doc nav, and we can go look a little bit more into the lockstep feature. Doc nav. I need to load the documentation. But yes, there is a lockstep feature. Let me grab the user guide for that. Okay. Yep. So lockstep operation. Okay. With two or more identical MicroBlazes to execute the same program, but kind of outputs of the cores and any tamper EPTIS detected. Here we go. This is what we probably want to look at. it'd be interesting to find an app note about how to do this. But here's the example that's listed for the lockstep. Okay. We're probably going to have to end the stream soon. So if you got any questions, I can answer them in about the next 5 minutes. But thank you for joining. If you want to continue to follow this content and future questions, I am FPGA Zealot on YouTube, X, Twitch, or Andrew Wilson on LinkedIn. We had a really good question from Vivado on YouTube. Is there an official HyperRAM IP core? AMD currently does not have an official HyperRAM core. I am currently working on my own. So hopefully, I put it on GitHub. You can look at some of my posts on LinkedIn or on X to see about that. I'm going to try to get a lightweight, high performance HyperRAM controller up and running, and just show the source for it and how to use the high-speed interfaces. So yeah, look forward to that. I'll post more about that in the future. Yeah, I'm gonna wait 5 more minutes. I'm probably gonna end the stream. But once again, thank you for joining. This is a fun experience. I really like sharing, I guess, my passion for FPGAs and the fun stuff you can do with them. And if you have any suggestions for future videos, please post those in the comments. I would love some good feedback. Oh, PCIe. So we'll have to look at that. I need a good dev board to show that. Mostly it's hard cores for PCIe. There's not much in PCIe soft cores. Well, I'll definitely do some. Oh, I would love to build a PCIe switch. So YouTube we comment talking about PCIe hard cores, soft cores, and a PCIe switch. I would love to do a PCIe switch example. We're probably there's not a good development board to demonstrate that off, but I would love to demonstrate that. Yeah, like heart these comments. Nope. Here's a heart. Yeah. Oh, so no YouTube comment about setting up the Ethernet in the SoC. Yeah, the next example, I would love to do that. We do need the HyperRAM for the LWIP library. If we want to, support the whole UDP TCP stack, we need more instruction memory space. But that would be a great example to show. Okay, I'm just going to change this to the first tab and wait till the video updates on all the streams. Okay, doing good. Okay, I'm going to probably end up closing. I don't see any more comments. Thank you for joining. Feel free to watch this VOD on LinkedIn, YouTube, or Twitch. I do enjoy multi-streaming. If there's any other platforms, I may explore those in the future videos. Oh, that said Tiny Beast. That wasn't supposed to be Tiny Beast. Okay. Okay, thank you.